Welcome back for another video on the E-6B. Today we are looking at an example from 1942, manufactured by the Cruver Manufacturing Company in Chicago, Illinois. We know a little bit about the dating of this device for two reasons. One is that the U.S. Army Air Corps changed its name to the U.S. Army Air Forces in June of 1941. And Cruver Manufacturing had the year of the order as the first two numbers of the order. So we can see here that this was an order from 1942. Now, Ben Rao, who was the president of Felsenthal, wrote a nice article on the history of the E-6B in the Navigator. And he wrote that in April 1942, the first of many sizable contracts for the E-6B was placed. There was roughly 40,000 E-6Bs that were ordered. We also know that in November of 1942, the War Production Board introduced the Controlled Materials Plan, which put limitations on the use of steel, aluminum, and copper. And Rao writes that it was only by sheer luck that enough aluminum sheets and some brass sheets were located to complete the orders. And so what we have here is one of the rare brass E-6Bs. And you can tell that this is one of the brass models by looking at the edges of the device, where you can see that brownish orange color as some of the coating has worn off. Anywhere where the device would have touched a surface, like here, as this would have laid on a table, you start to see that golden color. And especially if we pull the slide back and look at the back side of the body of the device, you can see clearly that this is a nice bronze color. In order to be really sure, though, that you've got one of these rare brass E-6Bs, you could throw it on a scale. And so let's go ahead and do that now. So this brass E-6B, when we drop it on the scale, comes in at 284 grams. And if we compare that to the original aluminum E-6B, that comes in at 126 grams. So the brass E-6B is more than twice as heavy as the aluminum model. All right, let's do a comparison on the front faces so we can see the things that have changed here. We've already talked about the name, but other than that, not much has changed. So we have extended ranges for pressure altitudes on the altitude and airspeed corrections. So we can tell here that the pressure altitudes ended on the original device at 30,000 feet, whereas here on the 1942 model, they go all the way up to 38,000 feet. And that's the same as well for the air temperature. I'm sorry, the airspeed. You can tell that this stops at 30,000 feet, and if we roll over to this device, it goes up to 38,000 feet. We also have slightly different directions for the altitude corrections. They're simplified in the new device. So in the original, we have this little caveat that says, if ground temperature is known, set mean air temperature opposite mean pressure altitude to get better results. That was removed in this 1942 model, where it just says to set the flight level air temperature opposite the flight level pressure altitude. So let's actually do an altitude computation to see how this works in practice. So here are givens. We have a pressure altitude of 4,000 feet and an outside temperature of minus 30 degrees Celsius. So we have 4,000 feet. It's this second mark right here. So 0, 2,000, 4,000. And we have to set that against, hard to see in there, minus 30 degrees Celsius. So we'll set this up just like that. Next, we find our indicated altitude, which is 4,000 feet on the inner dial. So that's right here. And then we read our true altitude on the outer dial. So that's going to be 3,000, 1, 2, 3, 3,000. Where are we here? Got a little bit of a, turn the dial a little there. So 3,456, about 3,460 feet. So that's a significant difference between the indicated altitude and the true altitude. And that's why pilots learn when temperatures go from high to low, look out below, because here our indicated altitude is much higher than what we think. Let's take a look now at the wind side of the device. A couple of differences to note here. So first of all, the slide is now using green ink. I don't know why. I happen to like the green ink. I think it looks nice. And we have this handy device here, which is a lanyard attachment. So airplanes can be bumpy places, and a navigator's desk would have been full of all sorts of important instruments, and this was a handy way to secure them. So today, the problem that we'll do on the wind side of the device is an old school winds aloft problem. You can imagine that we're flying over the ocean, we don't have any radio contact, and it's up to us to figure out what the true winds are at the time. We would have done that with a drift meter. And so a drift meter allowed the navigator to look out the plane and compare what the patterns and the waves were doing with the flight path of the airplane, and you could determine whether we're drifting 3 degrees or a number of degrees left or right of course. So in this example, let's assume that we're flying a true heading of 090. And as navigators, we take a drift reading and find out that we're drifting 3 degrees left of course. We then ask the pilots to turn us 45 degrees right of course, and that would give us a heading of 135. And there, we would have noted that we had a drift of 8 degrees to the left. Then we'd ask the pilot to turn 45 degrees to the left of our original course, which would be 045. Take another drift reading, we would have gotten 3 degrees to the right, and then resume our initial true heading of 090. So what we need to do is we need to plot these 3 drift angles, and when we do that on this device right here, then we will find our wind direction and our wind speed. So let's go for it. What we need to do is we need to set our true heading up at the true index. So we'll turn this until it says 090 at the top. There that is. And now we will plot our 3-degree left drift angle. We also need to set our grommet here on our true airspeed, which is 150, as indicated on the problem right here. All right, 3 degrees left, so we just count the squares, 1, 2, and 3. So that's where that drift line is, and what we'll do is we'll pencil it in here, like this, just going up that drift line. Then we roll in our next heading, which is 135. Bring that up to the true index, 135. Here we had a drift of 8 degrees to the left. So we have 5 degrees, 6, 7, and 8 right here. Draw another drift line. And finally, we turn to a heading of 045. This brass wheel is a little tough to turn. And we had a drift angle of 3 degrees to the right. So we just count 1, 2, 3, and we draw our drift line up from there. And where these 3 lines intersect is the location of our winds aloft. And in order to find that direction, we roll it to this mark, which I'll make it a little bit clearer for us. Put a circle around it. We spin it so it's at the bottom of the bezel and lined up with the center of the device. Just like that. And that's when we can read the direction of the wind from the top of the device. This looks like 250 to me. So that will be our wind direction. The wind's coming from 250. And our wind speed, we can find by putting that dot on any convenient sort of marker. I'll put it down here on 100 and reading the distance up to the grommet, which is right here in the center of the device. And that looks to me like it says 124, so a difference of 24 units or 24 knots, and that is our wind speed. So that's how we would have found the winds aloft from 3 different drift angles. All right, one last difference that I want to note about the 1942 E-6B here is that, sadly, it's missing the name of the inventor. Philip Dalton's name no longer appears on the 1942 device. And tragically, Philip Dalton never would have actually seen this device. He died in July of 1941 at the age of 38 in a flight training accident with a student. And he would never know what an impact his design, his flight computer, would have on flight training for the next 80 plus years. So one thing that this rare brass E-6B does make clear is that in 1942, manufacturers had a problem to solve. If they couldn't find enough aluminum or enough brass sheets, how would they make enough flight computers to fight a war? If you want to see what they came up with, check out my next video. Thanks for watching.